I'm Le Ferrand. I'm a computer science student out there in Paris, and today I'd like to talk a little bit about distributed computing, but not exactly in the same fashion that JoCaml-powered did a few hours ago. Here we are going to talk less of a cluster and much more about desktop grid. That is, desktop grids are grids built with very heterogeneous resources, such as personal computer and server connected through the internet. It's not cluster. In fact, I started the project a few months ago. I was interested in architecture and design. Architecture for building houses, not CPU. And as you may know, more and more architects are using 3D rendering software, ray tracer, to preview their work. And it's a very CPU intensive task. So they want to parallelize it, but they often can't afford a dedicated cluster. So I thought that it was perhaps possible to build a web service for those architects to share their CPU and memory. So most of the time, when they are not in their offices, they connect to the grid and they offer their CPU against credit to other users, and when they want a burst of power, they request power from other users. And when I had a look to the existing software, I thought that would be a nice idea to write my own and start a web service using NACL Grid. So now I'm going to present this software. So what do we want to do first? We want a scheduler and a resource manager that can handle various power sources, such as dedicated server, local computer, personal computer, and perhaps extra server that you can rent on the fly from a cloud, for instance Amazon EC2. And this introduces strong constraints. Those new constraints are flexibility. We want to be able to add nodes on the fly and confiscate during the job. We also want a strong security feature, because if you want to convince a sysadmin that he can authorize its user to share their computer in the grid, you have to show him, to prove that the host application is not going to corrupt the file system or be used as a botnet or something like that. You need some security feature. You need to be able to handle heterogeneity. Computers are not clones, so every computer is different one from each other. They might be connected through the internet, not InfiniBand. You're not in a cluster, so you have to be able to handle this diversity. And then you have to get something stable. So you have to get, it's much more. It's a resell point. And you have to. My software is supposed to work. Thank you. And you're supposed to be able to port existing software to this new architecture pretty easily. If you need 10 years to port existing software, then it's useless. So what are we going to discuss today in the few minutes I have here? First, we have to focus on the distribution process. This is how we are going to. What will be the life and death of a job, and then we'll see the overall architecture, software architecture this time, of NACL Grid, which is the grid engine. And then we will see an application of this grid engine called the Collaborative Rendering Farm, which is a web service I've started a few months ago. Okay, so let's start with the distribution process. It's very easy. In the grid you have several nodes, and they are all they have all the same rights, and each node can start a job. It can start computing on its own, and then it can start dropping tasks on a central server, saying, okay, this is the input, this is the name of the function you have to apply on the input, and you give also the name of the application. So with the small OCaml record here, and nodes that are idle, that can fetch tasks and return results to the server. All of this is done through HTTP, because my first server were the server from my school, and they were behind a proxy, so I had to implement that over HTTP. Then I had My account was blocked, but not an issue. So the pros and the cons of this, it's very simple. It's slightly more flexible than MapReduce. MapReduce is a distributed computing framework where you can also span tasks and fetch results, but you usually apply the same program to each input. And it fits the constraint because you can implement many software with this simple pattern. And the cons is you can deadlock. You can lock the grid if you don't know what you're doing. But there's a bit of inertness, but this is not very important. This is a life and death of a job, a very simple job. As you can see, the node starts the job. It computes alone. It does pre-processing or whatever. And then it decides to forward 2 tasks, connect to the server, hello, I want that, that, and that done by other nodes. And nodes that were idle were keeping polling every let's say 30 seconds, and there's a task. So they download the job, download the input file, and the application code, they perform the task, and then node A is able to fetch the result. To do this, the central server has a very, very simple REST API over HTTP. As you see, you have connector to start job, drop file, fork fetch, and stop job. The first connector are usually used by the nodes that start the job, and the last 2 connectors are used by the node that perform the job. And of course, this is not directly used. You have a C, C++, and OCaml API for that, or library, I mean. And this is sufficient to do a lot of things, especially 3D rendering. In the 3D rendering process, you start by analyzing your data, building something called the KD tree from the scene to intersect the rays and the scene. So it's a very heavy application. Do it on the central node, and then you split the image on tiles, 1,000 or hundreds of tiles, and each agent process a tile, and the master node assemble the results to get the full image. So this is a distribution process, and what we have to do now is to open Emacs and to implement it. So, this is not vectorial image. So okay, so there are 2 parts. There is a server and there are the agent. It's a client-server model. If you want, we can talk a little bit why. We will talk later on why it's not peer-to-peer or something like that. But basically, you need a lot of bandwidth, and in a peer-to-peer model, agents usually can download very fast, but they can't upload very fast. So client-server architecture is much suitable. So you have I'm sorry, it's blurred. You have a server, which is based on the Oxygen web server, by Vincent. And there are a lot of plugins for this server. There's a job manager that handle the job queue. There's a tracker that track the agent and is responsible for failover because agents can crash. So you want to reattribute a task. There is a user management system with a billing application, and you have a resource manager. So the resource manager is responsible for handling both the volunteer, that is the people that share their own computer, and the resources that you are going to launch on the fly. In my case, it's into Amazon EC2. And of course, you need an agent to perform the task. So there are 2 kinds of agent. There is a very specialized agent that is designed to handle a single task. That is 3D rendering. So it's an application that does 3D rendering. No problem with that. But you also have a client, a generic client for the people that share their own computer and that want an extra security layer. And it's based on the Google Native Client Sandbox. I don't know if you know this. It's still quite experimental, but it's already functional and efficient and working. You get a special compiler from Google that compiles your code, C, C++ code, or OCaml code directly to x86 instruction, and that replace all the system calls by calls to a plugin. So you get a binary that is going to run on Intel computer, Mac OS. Same binary will work on Mac, Linux, and Windows. And the plugin will be responsible for tracking the system call and authorizing some system calls. You want to know the date, but forbidding other system calls. You don't want the program to access directly to the network. And the good point with the fact that with the Google Native Client is that you get a very generic architecture. You can deploy any application without asking the user to reinstall a client software. So it's very easy to deploy any application. It's binded in OCaml. Just I could. Current client code is Necklace. So it's a C++ client. This version is a C++ because I'm very bad at writing GUI. I wanted contributor to do it, and I couldn't find any contributor in OCaml, so I wrote it in C++. And the server side is implemented in JoCaml. JoCaml offers OCaml plus Giant Calculus. It offers a nice framework for both for concurrent programming and personally I enjoy this language, so I choose it to handle the job queue. It's very straightforward and the code is very readable. And yes, the distribution feature of JoCaml are used to enforce the stability because you want to host third-party application on the server, and you don't really know when you host a C++ application binding in OCaml if it will really work for a month or if it will crash one day or another. So it's better to fork or to start a separate process. Start a separate process connected through JoCaml, and if something crashed somewhere, it will be the JoCaml child, not the main process. This is how the core farm has been running for about 5 or 6 months without restarting the server or anything. So now we have a software called NSL AC2, and we want to deploy it. There are two versions of it. There are two versions of the deployment called the core farm. There's a version which is currently online at www.corefarm.org, and which is only for volunteer computing. That is, only the people that decide to share their computer can access the grid, and it's only working on personal computer. There is something like 700 registered users, but much less people contributing, but maybe 20 or 30 people contributing right now. So it means if you start a rendering job right now, it will run about 20 times faster, so it's already interesting. And there's a new version that has been deployed 2 days ago, but it's not really public, and it's deployed in Amazon EC2. So Amazon EC2 is a cloud by Amazon. Amazon is the bookshop, retail shop on the internet, and they have a lot of computer. And somebody one day said, "Oh, but we have a lot of computer." And when we have a look at the usage pattern, they are used only between Christmas Day and New Year's Eve. So say, "Oh, but we're going to rent them the rest of the year." And they came out with something called Amazon Elastic Cloud, where you can rent server on the fly. So the NSL grid is deployed on the gateway. Currently, there is only one gateway at the entry point of the grid, and when somebody wants to launch a job, for the moment, you only have the rendering application. The people who launch a job can ask for a certain amount of computing power, and NSL grid will start the agent on the fly on the cloud. We're going to launch one just for fun, just to see if it works. You can't really know. It doesn't. Okay, how can I escape that? I escape. I want my browser. Okay, so this is the Amazon Web Services console. Right now, I have only a server up. It's my gateway. It's behind the load balancer. Here I can start 1,000, but I don't want because I'm going to pay for that. So I start only one. And now let's say I want to start a rendering job. So I don't know if you're familiar with something called Blender, but it's that. And you have a plugin called Yafar Export, because the rendering engine is a distributed version of Yafar I wrote in September. And you say, okay, I want to render this job. It's an architect job. I want to put on the core farm. I want 10 core. And I render. And right now it's uploading the data on the server, so please stop downloading, uploading, because I need a lot of bandwidth. Okay, so I will go back to the slide, and in a few minutes you will see the additional instances up, hopefully. Hopefully. Hop. So it will be released publicly next week, probably. I have to write a nice interface for that, based on the current website, and to do some tests before, I suppose. This is the current collaborative rendering file. The interesting point with the NSL EC2 is that you can launch almost any application on it. I mean, given that you wrote it for the grid. So currently there is only the rendering engine, but supposedly anyone can write his own application. I know that in CERN people want to do some analysis, data mining on their big files for on a grid like that. So it's not entirely released as an open source project yet. There are some libraries, especially all the libraries that connect to the Amazon EC2 cloud and Amazon S3, Amazon SimpleDB. And the core application will be released as an open source project too, but I still have to solve some issues. I mean, it's not that easy to install a JoCaml compliant Oxygen web server, but it will be. It is, it's simple, it must be a bit more sure. And there will be also a developer website with a sandbox where you can start your own job and see what happens. But it requires a lot of manpower, so if somebody is interested, you're welcome. Let's have a look to the Amazon EC2 instance is... oh, no new instance. Aha, 2 new instances are in pending state. They are starting. This one. So the job will be launched on those 2 new servers. My bank account will be totally empty after the end of the demonstration, and I will receive an email when the job is done. And then I have to fetch a result in Amazon S3 storage engine. Okay, so here it is. It's a simple application, like it's written in OCaml. And to conclude, just want to emphasize why I wrote it. Yes, I emphasize why I wrote it in OCaml. Personally, I do it because development time is much shorter compared to C++. I might be a very, very bad C++ programmer as well, but it's really shorter, and it's very easy to explain to non-developer. You want to show the code, it's much more concise, much more shorter. I tried with non-OCaml developers, say, oh, this is the functions, okay, I understand this software architecture. The only problem is that it's difficult to find contributor. I had the same issue with a web service I wrote 2 years ago called BWiFi. Was a captive portal written in OCaml for Windows. And I don't know if it's as difficult to hire to hire people as well. Finally, I want to thank the Gallium team for OCaml, because it's pretty nice, very nice tool, and DPS for Oxygen web server. And this is one of the jobs done by one of the architects on the core farm. It's supposed to be a high resolution job. It's about 200 hours on a single computer, and it's about 1 hour on my university computer. So if you have any question, please ask, or you have my email if you want more details. Thank you very much. I don't know if the job is over on the... okay, this was the expected result. There is a color issue on the projector, but the result was supposed to be that. It's an interior of a restaurant by a Finnish architect. Okay, so if you have any questions...
Just a small question. you answered the question why OCaml, so could you also answer the question why JoCaml, or did you also test the other frameworks or other possibilities? So if you could just give some pointers from a practical point of view.
From a practical point of view, I wrote my first JoCaml program a few years ago, and I get used to this, so it was so natural to use it for NSA grade. I think it's more a question of personal feeling than performance. Why JoCaml? It's pretty easy to write concurrent software and get something very clean without having to write log and log mutexes by hand. So I find it very convenient. And I also appreciate the distributed feature that allows you to connect a remote instance very easily. You don't have to write by hand the marshalling serialization process to send object from an instance to another. I suppose perhaps other libraries offer this as well, but I stick to the tool and I enjoy it. But if you have more questions on JoCaml, don't ask them to me, you have Luc qui m'arrangeait over time. Okay, no more questions?
Did you mention that you have to use a modified version of the OCaml compiler to produce a code that can be run on the Google native client?
Yes. No. If you want to run code through the Google native client, you need a patched version of the OCaml compiler. Somebody did it and posted the patch on the OCaml list. So it's a very simple process. And
if you're interested to learn more about a native client, there's if you would like more details on native client from Google, there's a nice paper in Communications of the ACM a couple of months ago, or maybe not the last issue, but the one before. And the HTML versions are freely available online. So, and yeah, as far as I remember, so basically it asks for target of branches to be aligned on some power of 2, maybe 16 or 32 bytes, so that it can quickly check code pointers and return addresses for correctness. And so you need to change a little bit the way compilers generate code. Yeah, as far as I can remember, the OCaml patch was kind of straightforward.
at the administration console, there are 2 tiles completed on a total of 16. So it's a very heavy job, in fact. But it's running on the grid, no problem. Okay.
Okay, so thank you, William. I